All right, so as I said, today we'll be talking about some important models and some important resources that exist in natural language processing, specifically from the perspective of like machine translation. That means like, how do we translate? So that's an important NLP task, right? How do you translate from one language to another? And you know that there are so many apps out there that do that task. So we are specifically trying to understand like how these work high level and some of the important resources, some of the important models that are out there that you can utilize if you're like trying to do any such task. So that's the focus of today's lecture. Let's get started. So sequence to sequence models from the perspective of machine translation. So there are many different models that exist when we're doing the sequence to sequence translation. For example, like you have some input sentence in some language, and then you're trying to convert it to some other language, right? And the way this has been done is like through two different techniques, and I've listed them here. Now, the very first technique is statistical machine translation, or SMT for short. So what you do is like you use some statistical models to translate from a source language to a target language. And so those are like, in general, known as language models. And then the second one is the encoder-decoder architecture. Now, what we do in encoder decoder architecture is that you'll have some RNN that is going to encode a sentence, and then you're going to decode it word by word, depending on the probability of like what is the most likely word that you should be translating into. Okay, so let me just like draw a high-level architecture of that here, what language models are and how the encoder decoder thing works. Okay. Okay, so we are familiar with RNNs, and so like you have some hidden, and so then H1, like the first hidden cell. This could be an LSTM, GRU, depends on like what we're doing. So let's assume that this can be like LSTMs or GRUs or anything, right? And so the way this encoder thing works is that I'm going to encode some sentence. Let's say this was the first word in that sentence, and let's say this is like French or Spanish, and I'm trying to convert it to English. So that's the goal. And so what we're doing here is an encoder to decoder structure. And why am I talking about this? Because this is basically using a neural network to learn, right? So I'm going to create like, let's say I have another hidden layer and then so on. And eventually I have like some final H sub n, right? And I get some output from this. Let's say this is like a complete RNN, and these are like multiple words that are going in. And so this part, this RNN that we have seen before, is known as like an encoder. So we call this encoder because let's say this sentence with like these multiple words was in French, right? So what I did was I created an RNN or a neural network representation of that sentence in French. But now I need to get the translation of this in English, right? So in some way, I need a decoder part that's missing in this one, right? And so for machine learning, for machine translation type tasks, that's what you need to do here. So you need a decoder architecture. So how does that like decoder works? The way it works is that like once like given this input, which maybe I can like in general called X, and maybe I've saved it in some ways, in some object, in some vector, I don't know. I've saved this representation somewhere. And now given this input, given this representation, right, I'm interested in like what is going to be the first word in English language when I'm translating it, right? So basically, I'm trying to get the probability of like this first word. Let's say that first word is y1, right? Given this x. Think about it like that. So this is how we model this entire thing, right? So the decoder is like nothing but another RNN, right? But the only thing that RNN is doing is that it has this entire vocabulary. So we're familiar with that idea, right? So you have this entire vocabulary. You're picking the most probable word, but it is a conditional problem. It's a conditional probability problem because like you're given this input and then you're picking. It's not like you're picking any random word. So most likely you'll pick the one that has the best representation in that other language. Okay, so let me just draw what happens here. So basically what you're going to do is, and let me stick to this right notation. So let's say you'll have like this input coming up, and then you'll have like the first word y1, depending on this. And of course, you will have some neural network, something here that you use to like decode that. And then using this input, you'll have like another cell, right? And then using this input, you input that as well and the hidden state. And then you get y2 and so on. Like we'll talk about how do we get y2 and like further. But high level, this is the encoder decoder architecture. And so this is used mostly for machine translation type tasks. Okay. All right. So high level, like, is this architecture like clear to everyone? Okay. So now going into the intricacies of this like encoder decoder architecture. As I said, this is like a conditional probability problem in the sense that I'm given some input and I'm trying to get some output. But the only thing is that I'm trying to get that output in some other language, right? And so the most like finding the when I arrive here and I have like some output at this point, the way I'll start decoding it, like getting y1, y2, y3, is going to be a sequential process in itself. And the way this sequential, because eventually what I need here, what I need is like probability of getting y1, y2, and so on up to yn, given my input x, like all the x's together. I'm just denoting it by x, right? And so how do I get this value? How do I get the probability of this given x? Well, I'm going to break it down, and from the idea of like independence, but like not complete independence, because I'll begin by like getting the probability of y1 given x. But once I have that, and I'm trying to predict y2, then the probability of y2 will be conditioned on x and y1, right? And then the probability of y3 is going to be conditional on x, y1, y2, and so on, right? So let me write it down here. The problem that we're trying to solve, and to be consistent with the notation, I'll keep what we're trying to do is we are trying to get this to yn given x. And the way we are going to get it is that I'll take each of those time steps as something that's independent from one another. And so I'm going to get these probability values, right? And so as I said like y1 given x times the probability of y2 given y1 and x, and so on, right? And so, okay, like in terms of writing this down, all of this is good, right? But then I need to like compute these probabilities, right? I need to compute these probabilities. So if we think about it, what exactly am I trying to do? I have this input, some other language sentence, let's say a Spanish sentence, and I'm trying to convert it to an English sentence, right? And the way I will do it is that I want to have the most probable choice of words, the most maybe frequent choice of words, or something that like justifies my selection from this new language, from this other language, right? So in some ways, I'm trying to solve this optimization problem that I somehow maximize this probability, right? So what I'm trying to solve is this like argmax over all the y's, this probability of this conditional probability of getting n given x. Right? So the words that maximize this probability should be my eventual goal. Because obviously in the other language, there could be like multiple ways of representing these words. And so my goal is, regardless of whatever it is, my goal is this. Okay, so the moment we see like an optimization problem, we know we want to solve it, right? And sometimes like specifically with like probability type objective functions, it's not easy to solve these. And like it has been proven why we cannot get an exact optimal solution and things like that. Anyways, like this is a probabilistic objective function. And so in order to solve this, obviously we need some heuristic or some algorithm or some way of like solving it, right? So one could be like a greedy approach. Like that's the first thing that comes to my mind whenever I see an optimization problem. Because like if I have some representation of this like French sentence, let's say I have it in a vector or something, right? Then what I'll do is in my English language, I'm going to see based on all those words, what is the one that's used most frequently? Because maybe I'll have like the English vocabulary with me. Maybe I'll have some text in English with me, right? So by like greedily, I'm going to pick the one that's like the most, that has the highest match with this X. Because I mean, because I can do it, right? So that's like a greedy approach. And of course that can be done, right? So there's the first approach to solving this problem could be a greedy approach, right? So once I've picked that, then that the next word that I'm going to pick, like the next Y2, is going to be conditional on that, and so on. And this technique is shown to like in many papers, you'll see that this works quite well. But the issue that comes up is that sometimes, like when we're doing translation, we usually like the results that we get. Let's say I get a sentence, an English sentence, and we usually match it with like human translation to see like how good it was, right? And so when we try to like measure that, then usually with a greedy approach, we end up selecting words that were like that are very common in English language, like things that we use in our day-to-day language, but they're not considered as good from the perspective of like a good representation of that, right? For example, I can say like for, let's say there was a Spanish word for like visiting, right? And I came up with going for that in English instead of visiting. Although like from the language perspective, visiting would have been more concise and more like to the point for that particular word. But I picked going because that's what we use in our daily language, right? I'm going there instead as opposed to I'm visiting there. So that's why this greedy approach is shown to be less efficient as compared to like other approaches. It's what that exists. All right, so let me keep this and go back to the lecture notes to see if I missed anything before we move on. Am I sharing this at all? Like people who are online, are you able to see my screen? Okay, so what just happened? Why it stopped sharing that? Okay, WebEx is behaving weird for some reason for the past couple of days, but yeah, this is what it is. We cannot do better than this. All right, so yeah, we talked about like how generally speaking sequence-to-sequence models work, right? And then there can be different architectures. We are focusing on the encoder-decoder type architecture. And this is the source paper from which I got all this information, just in case you thought that I'm making this up. So that's why I have the source. And yeah, you're like welcome to just go and read through that and get the details, right? So now coming to the other popular algorithm, that's the beam search. And to be consistent with notation, I'll try to follow this. The second one, this is like an important algorithm because what we do is that instead of like greedily picking up one most probable word, we select a range of words and then we create like replicas of the same network with the encoder-decoder network. And then we try to solve this problem. And then of course we pick the most, like the one that has the highest probability value, but still we're doing it in a more systematic way. And that usually is shown to get better results as compared to the greedy algorithm. Right, so and I'll show you high level. I have pointed you to the in the readings, the paper that talks about this. Beam search in like detail is there, but I'll still give you like a high level idea of like how this works. Okay, so beam search essentially is like you pick a size, a beam size. So let's say I picked a beam size of let's say 3, right, or 5. So what will happen is I'm going to pick 5 most probable words from the English vocabulary and then compute the probabilities. And then it's more like a depth first search, I would say, because then once you have like picked the most probable ones, then you'll go again into the vocabulary and pick the, like in the second step, pick the pair of best most probable words, and then 3 pairs and 4 pairs, depending on like how long the sentence is, right? So it's mostly like there's a tree-like structure that will get created, and then you're moving over that tree-like structure to get the best, the highest probability value. Okay, let me just like show you a high level idea. And so of course, like you'll have the encoder decoder architecture, and because it's hard to draw, so I'll just like write encoder decoder to like not draw that entire thing. All right, so let's say I have like this English vocabulary, right? So an entire like 10,000 words. Remember, that's what we said, like most likely words are 10,000. And like I have the encoder X with me, so the encoder did its part. And then using that, I have to pick some words from my English vocabulary, right? And so let's say there was some word X3 here and X5 and I don't know, X10. So I decided that my beam is going to be size 3, right? And so there are other words as well, but I just decided I'm going to have like 3 most likely words based on my X, like given X. So basically what I'm doing here is what is going to be my Y1 given X, right? And so this is just like the first step of my decoder architecture, where I just like, remember this thing that there was an encoder, and then the output of the encoder went into like the first block, the first time step, where I just like figured what Y1 is, right? And so instead of like just having one choice and like the most probable choice, I'll have like 3 of them. And then let's say I picked these 3, right? And then what I'm going to do is like for each of these 3 choices, I'll again go into my English like vocabulary. And then given this X3 or whatever my choice of word was, I'm going to solve this problem of like what is going to be the most probable word. And again, for this one, what is going to be the most probable word given X5 or given X10. So again, there is an added conditional probability thing there, which is making the problem more complex, but then I'm coming closer to the best possible representation because I'm basing my selection in my like decoder architecture, because like here, like this, let's say I pick this word, so then I'll be solving the problem of like, what is the probability of picking this like X11 given X3? So if this is the highest, then I'm going to pick up that X11. And so this like, as I said, this goes on and it depends on like how long we'll try to go. And so this is like a tree-like structure, right? And so eventually maybe I'll not even pick these words, but I'll pick like one of the paths that goes to the best possible representation of that sentence, right? So that's why like this works really well. And the only issue here, and like you can figure out what the issue could be just by looking at it. Like we know that this is a tree-like structure, all of that is good. Even if I decided to have my beam equals 3, right? Yeah, like just look at the number of choices that I have, and then like for every choice, the number of choices I have. Right, so you can just tell that there are issues. Well, we are going to address those issues. But for the timing, we are good because this works like in terms of like the quality of the translation, this looks good to me, right? So let me quickly go to the paper that what's the name of that? Okay, keep it. I think the first paper in the readings talks about it. If not, if I forgot to provide the link, I will do that right after the lecture, but still we can. This one talks about the encoder-decoder architecture that we just saw today. And I think, yeah, maybe I forgot to mention like these tags that you will see, EOS. So this is like end of sentence. Basically, this is like a token that you provide that like my input sentence has ended. So then start processing or invoke the decoder, right? And then here again, that token will come up and you know that you're done with like selecting these words. Okay, let me see if they have. So this is talking about the internal RNN structure that we have obviously discussed before. And here is like the problem that we are trying to solve, right? So as I said, that we are trying to find the maximum representation of this, which in turn can be written like this. And you know why it can be written like this? The right-hand side? Because each of those can be written as like the multiple of like the independent probabilities of like probability of y1 given x, probability of y2 given x, y1, and so on. So that's why the right-hand side looks like this. Okay. I remember this talked about beam search, or maybe I forgot. Okay, anyways, I'm going to point you to that paper as well once we're done with today's lecture. All right, so that's that. As I said, now that this beam search might have issues that like we have these probability values. And obviously, if you just go back and look at this thing, right? Like think about the magnitude of each of these probabilities, right? And like just to give you an idea of what I'm talking about. Yeah, so what we're saying here is that I'm trying to what I'm trying to do is like I'm getting these probabilities, y1, y2, and so on up to yn, given x. And so this should be like probability of y1 given x times the probability of y2 given x, y1, and eventually probability of yn given x, y1 to yn minus 1, right? And this like typically vocabulary size would be like at least 10,000, whatever language we are using, right? And so imagine like the values that will get computed for each of those paths, for each of those probability values, right? And so this can be like really small, right? Because we are multiplying them those small probability values. And so in order to deal with that, we have something that's known as like length normalization technique. So instead of like solving this problem of like doing an argmax of this thing, right? Because this is like like we are multiplying all of this, we can do a small trick here that instead of like multiplying them directly, we can sum them up, but we'll have to do some kind of like manipulation here, right? So what I can do is I can take the log of these and then sum them up, which will be pretty much similar to what I'm doing here, right? So maybe let me write it down here. There isn't enough space, but I'll still do. And then instead of like having the product of all of these, I'll just sum these up and take the log of like how to represent it best. P, Y, sum yi given x. 1. Yeah. So that should work well. And this is summed over all y's, right? So this is shown to work better than this like the product that we're doing if we are solving this problem. And even better, I can like even take some form of like the number of values that I have, right? So if I just like average them out and do the maths, that's shown to have like a more stable sort of structure. And in addition to that, you can even have some like hyperparameter, and then these are like just optional variations of this problem. But you can have a hyperparameter alpha here that has a value from like 0 to 1. So depending on that, like what weightage are you giving to the total number of words that like you're scanning, right? But then of course this is optional. But these are all techniques that can stabilize this a little more, this beam search. Is given the overall structure of beam search is such that you will end up getting those like very small probability values. Okay, so I think I have covered most of it. Let me see if I missed anything. Yeah, I think so. All right, anything that is bothering you or any comments? As I said, like today's lecture is more about like just jumping onto like these different topics because I just want you to be aware that these are some of the important research areas in machine like NLP. So that was that. And then let's go back to the lecture slides. Lecture notes. Okay. Why is it not opening for some? Okay, so I wanted to introduce like this metric for measuring machine translation tasks in general. As I said initially that like, let's say you translated a sentence, right? How do you know that this is a good translation or not? So obviously we have some like human translated sentences and we're going to measure like the quality of our translation with that, right? So in some ways that's what this like this blue score does. So this is bilingual evaluation under study. It is like evaluating your machine translated text against some given translation, see how good that is, right? And it's usually a number or it's a score between 0 and 1, 0 meaning like it's bad translation in the sense that there was no overlap with the given set of words, but like let's say 1 is almost a perfect translation, right? So this metric is important because that's how we can like understand how good our model does in terms of like translating something to another. The general idea here is that multiple studies have been done to see like given this text, what is my blue score, right? And usually with shorter, like if the sentence is extremely small, then maybe you never came close to that actual translation. And so you might do okay. And then some like optimal size sentences do really well. And then as your size of your sentence starts to grow, you can tell that like with models like beam search, for example, the quality of the translation will go down. So that's the high level kind of, let me just draw it here to give you an idea. Yeah, so let's say this is the length of the any sentence of the input language, right? So this is length of sentence, and this is my score. So this is my blue score. And let's say it's like really small. So usually the blue score would be some intermediate value. And then as the length of the sentence grows, of course, I have like more information about that sentence. So it should like ideally speaking grow, and that's what happens. That's the usual trend. And then it just like starts to go down as you have like, and I'm talking about the encoder decoder architecture. So what happens is that you have like this ton of information, and just notice how this encoder decoder thing works. I'm carrying over all that information conditional on the previous words up to the end. And then like I'm making those predictions. And as I'm going towards the end, I'm losing a lot of information. We've talked about this in like when we discussed LSTMs and GRUs, right? That was the issue that like, of course, I'm interested in all this context and everything, but then it eventually drops beyond a point because of this, like in LSTMs, GRUs, we saw that there was this like vanishing gradients problem, right? And like even in this encoder decoder, we have like these cells, these hidden cells that are carrying over information. And so eventually we'll lose all that information. So that's what this is indicating us towards. And so obviously we need better models to deal with that, right? And we do have better models to deal with that. And one such model is known as these like attention models or like attention based models. Now, high level idea of these attention based models is that like if we think about the way like humans translate, right? Uh, in encoder decoder, what we're doing is I'm taking this entire big sentence, creating a representation of that. So that's what like encoding is doing. And then I'm starting to translate that one by one. But instead of that, how about I take some information from that sentence and start like doing something with it instead of like waiting until the end. And also like keeping track of like which ones are the important ones, which are the important inputs versus the ones that are not, both of them. So that's the high level idea of like how these attention models work. And I'm going to show you again like this high level idea of how these work, or maybe we can go to the paper because this is an important paper, by the way. Okay, what happens to this every time I'm in slideshow? Okay, this is the other one. Okay, so this is a very well-known paper, and is this the one that talks about? Yes. So to some extent, it talks about the overall like how attention mechanism works. But before that, because we haven't looked at these bi-directional networks, so let me like talk a little bit about them and then come here. So this actually is an illustration of a bi-directional network. Now, what we have seen is a single directional network. Now, if you go back to the fundamental idea of like an RNN, for example, remember we had these hidden units, right? So that then there was like this H1 and then this H2 and so on, right? Up to Hn. And we had certain inputs, certain outputs. Maybe we can have like maybe we can use this here, or maybe we can have a new input. Both cases are okay, right? So what's going on is that I'm like continuously pushing this hidden information from one cell to another because I need to capture the context of like the previous word, right? But what these bi-directional networks, they do, and let me write it down, or bi-directional models, is that they will allow some information to pass backwards as well, right? So you have like this two-way kind of traffic that like you allow something to go ahead and you allow something to go back from this cell to the previous one, right? Why is that? Because like if you think about any English sentence, sometimes the context of like the current word could be found in the future words. Similarly, sometimes the context of my current word could be found in the previous words. And so that's the idea of bidirectional models. Again, they are similar to any RNN, except that like when we calculate the hidden state of any of these here, we think of this as like two things, like H1 going forward and H1 going backward, right? So you'll have a vector of like H1 being like H1 forward and H2 backward, right? So you'll have a representation of like both. So that's precisely what this is doing, just in case you are getting confused with like, what are these arrows telling me? So instead of like drawing horizontal, they have like these vertical cells for H1 and H2, right? So one has the forward arrow, one has the backward arrow. But regardless, they are RNNs, right? And so now going back to our issue with the encoder-decoder model, right? I said that we can have some sort of a attention mechanism where we can take care of like the context of like the closed words, and then maybe do some kind of prediction with like a certain set of words and then go to the next set of words, instead of like encoding everything all together and then waiting for the decoder network to get initiated. So that's a fundamental idea, and you can like tell just by looking at this picture. And let me just take a screenshot of this and talk through this. Okay, so again, the problem that we are solving is still the same, except that I have like this extra network that's sitting on top of this like attention mechanism, right? And what's exactly going on is that I have my like hidden cells. There's like this extra network that's sitting here, and there is this another layer to it that's sitting on top of it. Now what's going on? Let's notice like this X1 is my first word, right? And so for that one, I have like H1 going forward and H1 going backward. And then X2 is the second word, and then the third word, and so on, right? And each of these words, for like predicting the very first word in my translated text, will have some impact on that, right? Because remember the encoder architecture, what we said about that, like I encoded this entire input and I started decoding like the first word, the second word, the third word. So basically in this one, I'm not waiting until that point, but rather I have like these output cells as well present along with this architecture, with the exception that I'm taking some inputs from these like these hidden cells. That means, like now notice these alphas, like these alpha T1, alpha T2, alpha T3, and so on. So these are nothing but these are known as like the attention, I think, the amount of attention that like this cell T is giving for word one, amount of attention this cell, like this time step T is giving to the second one, and so on, right? So that's what these are. Think of these as weights in some ways, right? And you can tell here, so there's a soft max that's applied, so that's what this is, right? The exponential of some vector Eij, Eik. Let's understand that this E is something that we know how to calculate. I'm going to come to that, like how do we get it? But for the time being, think of these alphas as some weights for every time step that are needed for this particular prediction of this particular word. And so basically, I'm going to have like these alphas for the next word as well here, like some y t plus 1. I'll have like these alphas from each of these coming out here as well, right? And so what's like important is that I'm able to somehow capture how important these are, right? So some kind of an attention of these words for this particular word. Whether they were important or not, that's a secondary question, but basically that's what I'm trying to capture. Now, what is this C telling me? The C is actually the input. The C is the context for this particular prediction. So C is nothing but the summation of all these alphas for like from all the time steps, but for this particular I, for this particular word, which we weren't doing earlier, right? I had this like entire sequence of things and then I started predicting things. So that's the fundamental idea here. And this E sub, this Eij is more like like an outcome of these things here, these S's, because I'm getting like some kind of output here, right? And so think of like this E as like, let's say I have this input S of T, and then H, the hidden state that comes out finally. And then I have like this E computed on that, based on that, right? So that's the outcome that I get from like combining this attention mechanism and the input that's flowing on the top network. Again, I know there is a lot of like detail in this, and I'm trying not to like go into too much detail because you tend to forget. What I want, the key takeaway from this is just remember this the attention mechanism of these attention-based models is actually adding some weight to every single word in my translation, no matter how big that is. And so I'm able to capture the important points or the important part of the language or the text for the prediction of each and every word. If you just remember that much, that's enough, because I know that the implementation of these is pretty easy. That's good news for everyone. And you don't have to like worry about like these technical details. And I think there are packages for this one. I haven't personally used that, but I know that they exist in like almost all frameworks. Yes. So it's pretty much the same, but in my forward one, I'm also passing, like when I'm going forward and I've not started back propagation, I'm still like sharing information between every cell. And then eventually the back propagation would be the same. Yeah, so that's why I have like, let me show you. I have the bidirectional neural networks. And I think they're talking about training. If you just like go to this particular paper, they talk in detail about like how the back propagation will work. Okay. Yeah, that's why I didn't introduce that in class. I just introduced the usual recurrent neural networks because bidirectional are mostly used, and now they are being used. I don't know how many of you are familiar with BERT, but yeah, those types of models use bidirectional networks. And so you'll have to go into the details of like how that flow works. But think in the feed, when you're feeding them forward, then also that sharing is happening. Like you're going forward and backward both. So most likely my understanding is that even in the back propagation, you'll be doing some kind of sharing. But I don't remember the exact thing. So you might go into the paper, and if you getting stuck, just come back. We can So you're maintaining the states for each one of them, right? So like for one cell, you're maintaining two states. Is that the? Yeah, yeah, yeah. So that makes sense. Yeah. Okay. So where was I? Tension models. Okay. All right. I think I lost that page. Yeah. So my recommendation would be to just like try reading that paper at least. That's an important paper in machine translation, this one that talks about this attention mechanism. There are others as well, but this is, I think, the one that kind of introduced this idea pretty, like, I think it was in the 2014 or something, or 2015. But like going through this one would give you a good amount of idea of like how we can train these and how do we use them. But most likely the idea is that we have these alphas, and they are like in some ways representing the attention that you need for every word in your input for the prediction of a word in your output. So that's that. The other thing that I wanted to talk about, and yeah, I tried to put together as much as I could, but because NLP is vast and I cannot like have everything covered. So then these are like different islands, you can say, maybe interrelated, maybe not interrelated, but it makes sense to be aware of these just in case you're interested in working on any of these fields. All right. So then comes an important, again, NLP area, that's speech recognition. And speech, again, I'm not going to go into a lot of detail because if we end up going into the intricacies of each and everything, then that requires the entire like course on that. So I'm just going to go high level. So speech recognition or automatic speech recognition is actually the capability that you have human input language and you're able to convert that to text. So that's the specific problem I'm talking about. Of course, there are other variations of this that like things like trigger word detection, like for example, Alexa, right, or Apple Siri. So they're a part of this, but high level speech recognition stands for you have like human speech and you're able to convert that to text, right? So there are like many different papers on speech recognition, but I was interested in this one because this talks about a technique that's used, connectionist temporal classification, that's used for like speech recognition and converting it to text. So this is the keyword, or CTC. So if you come across that term CTC, you know that we are talking about speech recognition. Okay, so how this again high level works is that obviously I have speech data. That means my voice, let's say, will have been in some form of waves, right? And that needs to be converted to text, right? And just notice the way we talk, we are talking faster as compared to getting one word at a time. So this requires some sort of pre-processing, obviously. And once you're done with pre-processing, you'll also have to do some manipulation in your RNNs to capture that, right? So that's what this paper talks about. I'm not 100% sure if they have the picture that I'm looking for. And so this is showing you how they convert each and every word. For example, the, right? Just this exact small word, the, because somebody spoke that, and then the number of time steps that you might have in RNN might be extended, or they can be shorter, depending on how long you're taking to say that word, right? And so in some cases, what happens, let's say you're using a basic RNN to process this speech, then you will have to convert this the into multiple T's and H's and E's, and then have the blanks, because when you're speaking, it's expecting some wave to come in, right? And some signal to come in. So then that would be there, and then you'll have RNNs that are converting this to some output. And so there is this paper actually talks in detail about it. If you're interested in speech recognition, this is the paper to read. But the fundamental idea here is that you can use RNNs for doing that speech recognition. One issue that comes up though is that these RNNs, for example, if you're using trigger word type models like Alexa, then Alexa is actually looking for the word Alexa to get triggered, right? And so if you think about the RNN structure, right, the output that's going to be positive for Alexa is going to be just come up once, and then the rest of the times it's going to have zeros as output, right? And so those become really sparse or maybe imbalanced. And so there are techniques to deal with that. And so similar issues might come up in speech recognition. And so there are techniques to deal with that. But of course, we're not going into the details of that. I've provided the resource. Just feel free to read this. But yeah, let me see if it talks about. Okay, yeah. I think most of the language models still work on the idea of getting the probability values. Okay, the final part of today's topics that I wanted to cover was the transformer network. And the reason for covering this transformer network is because I don't know if you have anybody had a chance to work in NLP at all. You must have heard that term. It is a pretty hyped term. Transformers. Anybody knows anything about transformers? Okay, I see some people nodding their heads. You also know. So did you have a chance to work with any of the transformer frameworks? No. Okay. So yeah, I'm sure Google made sure that everybody hears about it. So that's why people heard about it. But yeah, it's a framework, I would say, created by Google, and it is used for mostly for tasks that we are discussing. So one could be this machine translation as well. And if you're doing a project related to NLP, I would definitely recommend people, anyone who's working on that, I'd highly recommend going into the details of the transformer networks, because almost every machine translation type task or predicting language type tasks are utilizing transformers. Okay, so what I decided to do was go over again the basic architecture of a transformer, how it works. And it is based off of this attention mechanism that we just discussed again. But there is a difference that they're utilizing this attention framework, and they're also taking some ideas from the database. If you're familiar with database things like query, key value pairs, so they're taking some fundamental ideas from there. So basically, it's a combination of these attention mechanisms, and also parallel processing of those attention mechanisms rather than sequential processing of those. Okay. So let me quickly jump to that, but I missed anything. All right, so this is the famous transformer paper that has like revolutionized NLP, I would say. So it's known as attention is all you need, and yeah, that is what it talks about. So what they're telling us in this, and obviously they show that the results are pretty, like they're really good based on like the existing models. So what exactly is happening? Let's quickly jump into that. So there are two things that are happening in these like transformers. Like one thing is self-attention. So not just the attention mechanism, but they are here taking it to the next level, and they're talking about something that's known as self-attention. And then the second thing that they're talking about is the multi-head attention. So two new terms that come up. And let me quickly show you the architecture if I have a good drawing somewhere. Otherwise, we can look at their own drawing. Okay, let's quickly. Okay, they are just talking about the stacked part, but I wanted to talk about what exactly are we predicting in this. So let me just write it down here only. Then we'll come to this portion as well. Okay, so what we were doing in the previous, like the basic attention type models, is that we needed to predict those alphas, right? And then bring them together and somehow get the C value and then get the final output for any given word, right? So instead of just those alphas, they like in this paper, they've defined this as like the attention is defined as like this uppercase A, which is a function of like these three things, Q, V, and K. So as far as I remember, this is the order. So Q is like a query, and K is like a key in a sentence, and V is like a value in a sentence. So based on like a query, key, and value, you get the attention according to their definition, according to this paper. So what exactly that is that you will compute this A or attention for every word. So for example, let's say I have like N words, so I'll have like A1, A2, and so on up to AN, right? And the way I compute this, and there is a formula for this, is that I'm going to pass it through a softmax. And so first I'll calculate the alphas only. Remember the alphas from the previous one. So let's say for any time step, for any word, P, T, R. And this alpha is like the exact same thing that was there in the attention paper. And I'm going to pass it through some softmax, which is like E, remember the E, T, T prime, and the summation. So this is just the softmax. Okay, so the alpha stays the same, but now I'm interested in computing this A here, right? And the way I'm going to get that A is by using this definition of this alpha, but a slightly, I would say, convoluted definition in the sense that I need a sum of a lot of values, and those values are exponent query K divided by the summation of the exponent of all the queries and then all the values, right? And then sum these up as well. Okay, let me show you a high level picture of what exactly I'm trying to do. Maybe let's go to slides. That's easier here. Okay. Right. See if I have a good. Okay, so why are we calling this like query and then key and value? So query is like the fundamental idea behind query is that, let's say I'm trying to predict a word X, right? And I try to query into the given sentence of like what this word is, or like is it like a location, or like I try to answer that question, right? And so the query is the question, and the way I'm going to answer it is that I'll use the key and the value pair. So is that key giving me some idea of like, is this representing a place, or is this representing a person, and so on. So that's the fundamental idea. So basically I need to get some form of representing the query and the relationship between like the key, because the key is going to give me the answer to that query, right? So the way I'm going to get it is that I have like these Qs for every word. So let's assume that I have like Q of I for the ith word. and I'll have a key for the ith word, and I'll have a value for the ith word, right? For every word, I'm going to compute these because based on this, my attention A will be computed, right? So the way I get these is that these are going to be some like parameters that I'm going to learn in my network, right? And have like these input X values. So basically think about this network where I have like X1, X2, and so on, right? And so based on these, I'm like getting these Q values. So like Q1, K1, Q2, K2, and so on. And eventually like whatever I have. And this like, so this is like the query thing where I'm asking the question, what about that word, or where, or who. And then this key is helping me answer that question. And value is the actual value of like based off of like the key and the query. Oops. Okay. So again, this is going to be some weights K of xi. And again, this is going to be some weights V xi. Sorry, xi, let me not have it like this. Okay. So what I do is I get like the dot product of each of these, right? And similar to my attention mechanism thing, I'm going to get the value of the word from like my some given dictionary. And I'm going to get some output from these and combine these outputs all together. So again, I'm not going into the details, just giving you a high level idea of like what's going on. So basically the thing that we said in attention is similar to what's happening here, except that I'm doing a dot product of like the query and the key, right? And so what, like, how does that help me? Well, it helps me because like this attention now is not just like a function of like the weights that are coming from the words, but it's a function of like, what is the context of this word based on this query? What is the answer I'm getting based on this query? And like, what exactly is the value of this word based on this query, right? So I'm like putting in like more rich information in my attention. So again, eventually we are going to compute that A that I talked about, right? And I'm going to have these A's for each of the words that I have, like so A1, A2, and so on. But again, this is computing the attention from different words based on their different contexts. And so that's why this is like another level above the attention mechanism that I talked about, because now we are basing our like entire computation of this attention on these three categories or these three things, and they provide more context to my attention mechanism or attention value. So once I have that, remember I said that we need to sum all of them up, and the paper also shows that. I clearly remember. So here, so it's talking about like, this is how I get the attention. And notice like this thing here, this entire thing is actually like what I wrote, the dot product of Q times KT, but like we sum all of them up. So for every word, I'm summing up the K, Q, Q, K, V for all the words. For just one prediction of one word in my translated text, I'm taking the input from all the words and then getting the output. Again, taking the input from all the words and then getting the attention. So I have the attention for each word. And based on that, I'm going to predict. Right? So think about it as like adding another layer to my attention mechanism. And then I'm not just done there. Like, so if we go back here, let's say you have this attention mechanism all figured out, all of that is good. Then what you do is you do this multi-head attention. Okay, I know that's like going too much, and that's why I decided to keep today's lecture short, because I know it's like a lot of information. And again, like I'm repeating, you don't have to remember all of this information as long as you understand high level what's going on and why these transformers are giving us better output as compared to the other models. That's sufficient as far as this course goes. So let me quickly talk about like what happens in like this multi-headed attention. So let's assume you have things like, so let's say you have figured your A1, A2, and so on, AN, attention for all the words, right? And what you're going to do is for every like set of these attentions, you're going to loop through the same input, but obviously you will have like different weights for like the Q, the K, and the V, right? And so like you're going to loop through this. Why you're going to get different set of weights, and eventually you will average them out or find the highest one. Because in every iteration, you'll be asking a different query. for the same word, but a different query. So then you get a different context for the same word. Then in the second iteration, you'll ask a different query for the same word. And then in the third iteration, you ask a different query for the same word. So basically, you've queried for the same word in like 4 to 5 iterations, 3 or 4 different aspects. And so you'll get more context to that word as compared to you would have gotten in a simple RNN, or even a simple like attention mechanism. Because the whole point of getting an attention mechanism was that I wanted the attention of all the other words to predict that one word. But here I'm going a level further. First of all, I'm having the query, the key, the value, and then I'm iterating over this multiple times. And every time asking a different question, right? And so every time I ask a different question, I get a different aspect of that particular word. And so I'm better at like predicting the context of that word as compared to I was earlier. And that's why like transformers work so well when we're doing any language related tasks, whenever we're doing NLP or other things. Okay, and then coming back to this like very weird looking picture. So this is just like this here is showing showing us how we've implemented it finally, like how they've implemented this entire model. And so you have like 2 stacks, and this is just showing you how they will be deploying this essentially. So even if you like don't understand that, that's absolutely fine. This is just like high level showing you that you have like 2 stacks, the one on the left and the one on the right, and they are like continuously interacting with each other, first of all. And each one of them, like notice this multi-head attention, like notice this orange box. So these 3 orange boxes, multi-head attention, are the loops that I talked about. So that has like embedded in it that model wherein we are continuously querying for the same word, but different context. So at least 5 to 6 times we query there, and then we get like the final attention for that word. And not just that, like once we are stacking these and to get the output probability for a particular word, we are like feeding this forward, getting through the multi-head, and then like again going into the next stack, have 3 more stacks there. And all of this is done like, so the justification for all of this is that this is the best possible like architecture for getting the best possible like output probabilities. So if you're interested in going into like understanding this, like definitely read the paper. If I remember correctly, they don't talk much about like why they have this structure, but they do talk about like how the information flows and what's going on. So yeah, I know as much as like they told us. So in some ways, but we do understand how this multi-head attention is working, right? And so we understand why we are getting a better output from transformers now. Because like the key takeaway would be, we know what an attention mechanism is, right? Getting the context of every word. And then we know what the attention mechanism in transformers is. Because we know that we can get context of the same word from like 3 different queries or 4 different queries or 5 different queries. And then we're using that context to get like the output in this particular transformer type model. Okay. All right, so that's transformers. And yeah, please like highly recommend reading at least this paper from today's readings. At least try going through this entire paper and see what's going on, like how the dot products in the weights, like how these are computed, these values are computed, and how these are estimated. All of that information is there in the paper. But as long as you remember the high level architecture transformers, I think you're good to use them. All right, so yeah, and so finally I have like 3 readings for you. As I said, definitely read the transformer paper. And then there are 3 more papers. And these 3 papers are the ones from where I like extracted most of the like material for today's lecture. So again, if you're interested in like really knowing the details of like how to train these networks, how we are like step by step doing each of these things, you can just like go ahead and read. But I extracted all the like lecture material from these 3 papers. So that's what the reading for today is. And yeah, I deliberately tried to keep today's lecture short. And so that's all I have, because I know that it's like so much information I gave you that it's like, it will take some time to digest. So think of these as like these extra tools that you have. Whenever doing some NLP task, you can pick any of these tools, go into the detail of that, and then based on like whatever problem you're trying to solve, you can just like pick that up and use it, right? So that's all I have for today's lecture. As I said, I made sure that I keep it short so that it's like if I talk for 1 more hour, then I'm sure everybody will be like dead here in this room. But I still wanted you to like be aware of these things as we go forward. And so that's why, otherwise, like I had planned only 2 NLP lectures, but today's one, like I just somehow decided to go ahead. I was still like double-minded, but then I thought, let me just introduce this. If any of you are like interested in more material, I can point you to like more resources as well. Okay, so that's all I have for today. And thank you for your patience for listening to all of that. But yeah, that's all I have. And just like a quick reminder, we have homework due today, and there is another homework that will be posted today, which will be due in 2 weeks. Okay. Right. Thank you, everyone.